Hello, and welcome to a video AI on finding the centroid of a solid symmetric composite shape. Given this solid cross-section, we need to find the centroid, or, in other words, the center of area. Our basic equation for the center of area looks like this. Area integrals of a distance divided by the total area. With composite shapes, we can turn this into a summation, and I have a similar equation for the y component of the centroid as well. Obviously, in order to compute centroids, we need to talk about an axis system. So we'll have an x and a y. We need to notice that this composite shape can be broken into three rectangles. We'll go ahead and number them for now. 1, 2, and 3, starting at the bottom smallest piece of the rectangle. And based on these equations, we can generate a series of column headings. We know we'll need the area of each piece, the distance along the x-axis and the y-axis to the centroid of each of those small pieces, and then we'll need the product of the distance to the centroid times the area. That will form the numerator. The summation of the area will form the denominator of our equations. Now we'll need to reference these x and y distances from some reference point. Since we have symmetry, since this is a symmetric cross-section, the smart idea is to choose a point that lies on that line of symmetry. Since we know that the centroid will lie on that line of symmetry, this will be our CPO, our common point of origin, in other words, our reference point. Let's consider shape number 1. It's a rectangle, has an area of 5 inches times 2 inches, and its centroid lies right in the middle. So we have a 10 square inch area. The distance along the x-axis to the centroid is 0, and the distance along the y-axis is half of 2 inches, or 1 inch. I'm doing the multiplication out for these two columns. Shape number 2, a total of 15 square inches. Its x distance also lies on the axis of symmetry, and the y distance to the centroid would be 2 inches plus half of this distance, which is another 2.5 inches, for a total of 4.5 inches along the y-axis. Again, doing the multiplication to complete these two pieces of the table. Shape 3. The largest rectangle, a total of 40 square inches. Its centroid again lies on this y-axis, the axis of symmetry, so its distance along the x-axis is 0. Its distance along the y-axis is 2 inches, plus this total distance of 5 inches for a total of 7, plus another 2.5 inches to find the centroid right there. 9.5 inches from that common point of origin. Again, multiplication completes these two columns. Now, in order to apply these equations for the centroid of the composite shape, we'll need to sum the area and these two product columns, ending up with these values. Now it's simply substituting these values into these equations to compute the distance to the centroid based on that reference point. So for the x distance along the x-axis, 0 cubic inches divided by 65 square inches gives us 0 inches left and right from the CPO. Similarly, for the y-axis, 457.5 cubic inches divided by 65 square inches, a total of 7 inches, or a little over 7 inches, up from the common point of origin. We must have this distance from the CPO in order to have this be a complete answer, because this point of origin, this reference point, is completely arbitrary, and depending on where you choose that to be, you could end up with a completely different answer, and it would still be right. Now let's briefly discuss if this answer makes sense. The x direction, or x distance, makes sense because we knew it should lie on this line of symmetry. The y distance is just over 7 inches, which is somewhere right in here. We know it would be closer to this large portion than to the small portion, and we know the center of this piece number 2 is 4.5 inches up, so it's somewhere above that. Seems to generally make sense. We know it's in the ballpark.